In this video, we're going to go ahead and introduce the wonderful world of trigonometry. We're going to begin with Unit 4, 4.1, radian and degree measure. Okay, so before we even go into that, a few really basic concepts. Okay, we have the definition of an angle, which is basically a ray. Remember, it starts with a point, ends with like an arrow type of deal. And that is being rotated about an endpoint. So like this would be the ray that got rotated this way, where this piece right here, the first side is our initial side, where the angle lands is the terminal side, the ending part there. Standard position is basically where the origin is the vertex and the initial side lines up with the x-axis. So anytime you have an angle that's starting from here and goes around, so this little piece of the x-axis here, that would be considered standard position. Okay. Few more things. We have positive angles and we have negative angles. Positive angles are basically those that go counterclockwise. So anything that goes this way, negative is going to go the other way. So clockwise. Okay. And more definitions. Lots of definitions for this first part. Coterminal angles. So these are kind of important. They're basically the same position of an angle where they have the same initial and terminal sides. It kind of works like a revolution. So you'll start like, let's say, well, I mean, this angle works. This piece right here is the angle. Going back this way is another angle, but they land in the same spot. Okay, so that's another way to think about it. Some different names that we can use for these angles or for any angles would be uppercase letters, so like A, B, C, D, etc., or Greek letters, such as alpha, beta, theta, and so forth. Okay, so hopefully most of this is review for you so far. Moving on, more definitions. We have the measure of an angle, so that's kind of what we're going to be dealing with mostly. The measure of an angle is basically the amount that we rotated from that beginning point to the end. So from the initial to the terminal. And we use radians or degrees. Okay, so the one that we're more familiar with is the degrees. However, radians has to do with, for instance, circumference, 2 pi r. We know that r is the radius. That's where the word radian comes from. So it kind of helps to show what is a radian. Okay, hopefully I can show you kind of a demonstration in class, but if not, let me try to describe it to you. 1 radian is basically the measure of from the center of the circle, so like central angle, think a circle, okay, that intercepts the arc, so the arc of the circle, and is equal in length to the radius. So think of it like if you have your radius, if I were to take that radius and wrap it around my circle, that's the radian measure that I'm talking about. So it wraps a certain amount of times around the circle till it gets to the length of your angle, okay? And if that's too confusing, like I said, we can try to show you something in class. Um, Please take a note that, and there's just some more definitions here, okay? Take note that there are about 6.28 radians around every circle. In other words, for every circle that you have, if I took the radius and I was somehow able to bend it and I wrapped it around my circle, it would wrap around 6 times and a little bit left over. That little bit left over is about 0.28, okay? 6.28 is approximately 2 pi r, 2 times pi, okay, and r being the radians. So that's where that formula comes from. Circumference, 2 pi r, is the distance around a circle because that's how many times the radius will wrap around the circle, okay? Moreover, 1 revolution, so remember revolution is kind of like, going around, is equal to 2 pi radians. So these are directly related. With that in mind, we have some things here that are going to help with some of the problems we're going to see later on. If we know that 1 revolution is 2 pi r, 2 pi radians, okay, well, half of that revolution is going to be 2 pi divided by 2, which simplifies to pi radians or pi r, okay? 1/6 of the revolution is, well, just divide 2 pi by 6, and that reduces to pi over 3. 1/4 divided by 4, this reduces to pi halves. 1/12 divided by 12, this reduces to pi 6, okay? And you can see here are a few visual demonstrations of what those look like. So for the 1/2 revolution, if you're going to go halfways, that's going to land on this right here. So that means that this piece right here, if I'm looking at just the top part of the circle, this is equal to pi radians. And that's why we have the pi right there. 1/6 revolution is pi thirds radians. So we can third, so you can see over here, and I guess I should have finished off the picture here. But if you continue to subdivide this, you'll see that we have 6 pieces, 1, 2, 3, 4, 5, 6, and each of those is going to be pi thirds of a piece because that's how much 1/6 of a revolution is worth. Okay, 1/4, well, we divided it into 4 pieces, so here's that one, 1, 2, 3, 4, and each of those is pi halves radians. Okay, and finally 1/12 comes out to pi over 6, so I didn't completely do this one, but if we subdivide this one, I always have a hard time doing this one. We will have 12 pieces, and each of them is pi 6 worth of a measure. Okay, so just a few visual examples of the ones we're going to mainly see in this class. Let's go ahead and try an exercise here and see if we can fill out this circle using the radian measure. Okay, you want to think revolutions. So notice that this one is in fourths. So we're going to look at that circle that we did that was in fourths. Okay, we started 0, and we know that the halfway point, if I go halfway, it's going to be half of the entire revolution. So remember, one revolution is equal to 2 pi radians, right? So if this whole thing is 2 pi, halfway is going to be pi. And the halfway point between 0 and pi, well, that's just going to be pi halves, pi over 2. Okay? If you're going to keep going, well, you have 0, pi halves, 2 pi halves, 2 pi over 2, which is the same as pi. Okay, what comes next? Well, 3 pi halves comes next. And if that's still a little confusing, you can also think of it as decimals. This is 0, 0.5, 1, 1.5, 2. But of course, we try to keep fractions when we're dealing with radians. Okay, let's look at the next one. Notice that this one down here has a bunch of other boxes, and it looks like it's going into, let's see, 1, 2, 3, 4, 5, 6, 7, 11, 12 pieces. So according to the one I had over here, it looks like it's going to be that 1/12 revolution. Okay, again, remember that 1 revolution is equal to 2 pi radians. So I'm going to start with the halfway point. From here to the halfway point is pi. Okay, half of 0 to pi is pi halves. Halfway from here, if you continue going this way, is 3 pi halves. Okay, and we know that this is in 12 pieces, so 2 pi divided by 12 is going to be pi over 6. So that means that each of these little ones is going to be going by pi 6. So this first one is pi 6. This one right here is going to be 2 pi over 6. Oh, pi over 6, but that reduces 2 pi 6. You can reduce that to 1 over 3 or pi thirds. So this is pi thirds. This one would be, let's see, 1 pi 6, 2 pi 6, 3 pi 6, but 3 pi 6 reduces to pi over 2. Okay, what's after 3? 4 pi 6. And I'm putting it on top because, again, 4 over 6 reduces to 2 over 3. So 2 pi thirds. Okay, what's after 4? 5. So 5 pi 6. Okay, so far you have 1 pi 6, 2 pi 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. This one right here would be 6 pi over 6. But again, 6 over 6 is just 1. 7 pi over 6. This would be 8. But again, we can reduce that. 8 over 6 is 4. So 4 pi thirds. 5 pi over 6. 9 pi over 6, but 9 pi over 6 is 3 pi over 2. It reduces. This one's going to be 10 pi over 6, but it's 5 pi over 3, 11 pi over 6, and then right here, 12 pi over 6, which again is just equal to 2 pi, which we already have. Okay. If you already made your foldable, one of the foldables you're supposed to make, let me go ahead and show you real quick. This one, the primary angles unit circle cheat sheet. Okay, you will see that pi 6 is actually one of the ones that we see a lot of. So pi 6 radians, which is the same as 30 degrees, here's that circle. You'll notice pi 6, 2 pi over 6, 3 pi over 6, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And you'll notice that we do have what they're simplified to. So for example, our 2 pi over 6 is the same as pi thirds, which is what I have right here. Okay, let's pick another one. Maybe this one, 8 pi over 6 is the same as 4 pi thirds. That's why we have this one here. So these are going to be real handy to know just kind of right off the bat. Okay, but this is why it works this way. What we're doing is basically dividing the revolution, one revolution, into 12 pieces, which each piece is worth pi 6 of a measure in radians. Okay, so let's go ahead and move on. Angle work now. This is example number 2. For these ones, we have to go a little bit back to our definition. Remember that coterminal angles is basically two angles that share the same initial and terminal side. So it can be going in the same direction, it can be going the opposite direction. As long as it lands in that same position, we're good to go. Okay. The key thing about this one is to remember that one revolution is 2 pi. So if that's true, all I have to do to get another angle that's going to land in the same spot is add 2 pi or subtract 2 pi. So let's make a note here. We're going to either add or subtract 2 pi. And that is all there is to it, okay? So let's go ahead and look at the first one. We want to find a positive coterminal angle. So I'm probably not going to subtract, because if I subtract pi thirds, remember pi thirds is kind of in the very first quadrant. If I subtract, I'm going to end up with a negative angle. So I want a positive one. So for this one, I'm going to add 2 pi, okay? Now we got to be careful because when we're dealing with fractions, remember you do have to put this over 1. So let's do pi thirds plus 2 pi over 1. And we have to have common denominators. So since this one has a 3, I'm going to multiply this one times 3, which is going to give me pi thirds plus 3 times 2 is 6. We want to leave the pi there, so 6 pi over 3. Okay, and now that they have the same denominator, I can add them. So there's an imaginary 1 here. 1 plus 6 equals 7, and we just bring the pi along with it. So 7 pi thirds is an example of a coterminal angle with pi thirds. And if we wanted to double check, remember that handy dandy foldable that we have, okay, this one, we do have one for pi thirds. Pi thirds, okay? This is pi thirds. My orange ones here are the positive ones. So if I follow the same pattern I did before, 1 pi third, 2 pi third, 3, 4, 5, 6, 7. And we don't have 7 written down, but if we keep going, it's just going to follow the next number. So 1, 2, 3, 4, 5, 6, 7. 7 pi thirds is going to land exactly on this same position. So it looks like we are good to go. Okay. Now you're going to tell me, well, why don't we just use this the whole time? And I mean, you can, that's fine, but we don't always have cheat sheet unit circles like that for every angle. Okay, let's try this one. Now let's just find a negative coterminal angle for pi thirds. So I guess we can use it for this one because we just did the work for the other one. So if I want a negative angle for this one, well, you're going to subtract 2 pi, right? So you're going to subtract a revolution. So let's do that. If I go here and I go backwards, okay, I'm going to go backwards this way. Okay, what is this going to land on? Well, We can also use the one we already have in here, right? This would be negative 5 pi thirds. I already actually have it written down here. Negative 5 pi thirds. These are my negative angles. So we could use that one. So let's use that one. Negative 5 pi over 3. And if you want, let's not put an equal sign. Let's just say we used the chart for this one, or cheat sheet, or however you want to put it. So that'll work. And I don't mind if you do that for one or two, but do make sure that you do show the work for at least one of them. Okay, so like this one we showed the work, this one we just used our little handy dandy chart. Okay, remember, same position, same initial side, same terminal side, revolutions away. Let's look at the next one. For this one, let's go ahead and show some work. Okay, so find a coterminal angle for 13 pi over 6. Now, 13 pi over 6, I know that that's going to be bigger than a revolution because 12 pi over 6 is 2 pi. So that means that this one went around and some. Okay, so I think I'm going to go ahead and subtract for this one. It doesn't specify, so I'm going to subtract just so I can show you a subtraction problem. This would be the same as 13 pi over 6 minus 2 pi over 1. We have to put it over 1. And then just like the two problems before, we have to have common denominators. So I'm going to multiply the top and the bottom by 6. Okay, and that's going to give me 13 pi over 6 minus 2 times 6 is 12 pi over 6. We combine the numbers, so the whole numbers, 13 minus 12 is 1 pi over 6. So my answer is pi over 6, and this is one possible answer. Just so you know, there are infinite number of coterminal angles you could find because I could have added 2 pi instead, right? I could have gone, I'm sorry, this way. I could have gone counterclockwise and said I'm going to add 2 pi. I'm going to add 4 pi. As long as it's in multiples of 2 pi, we could find many, many more. Okay, but I decided to subtract 2 pi, which gave me one possible answer of 2 pi over 6. Okay. Last one, find a coterminal angle for negative pi thirds. The theta equals negative pi thirds. So this one is just written a little bit differently. I'm telling you that the angle is equal to this. So I'm going to do the same thing. Let's go ahead and add 2 pi for this one. So plus 2 pi is going to be negative pi over 3 plus 2 pi over 1. We need to find common denominators. So times 3 times 3, negative pi over 3 plus 6 pi, because 2 times 3 is 6 over 3. There is a imaginary 1 here. So negative 1 plus 6 equals 5 pi over 3. And if we wanted to check that one, because we know this is one of the common ones, we could look at our pi thirds. Okay. And notice that negative pi thirds is right here. Negative pi thirds, and lo and behold, it is the same as 5 pi over 3. Pretty cool, huh? All right, next one. We have complementary and supplementary angles. So this is directly from geometry, okay? Complementary angles are basically two angles that add up to 90 degrees. In radians, we're thinking pi over 2, because remember that pi over 2 is like a quarter of the circle. So a quarter of a circle is going to be pi halves, or 90 degrees. Okay, supplementary angles is half of the circle. So pi, or 180 degrees. So we're going to deal with the radian measures, which is pi halves and pi for now, until we get to the conversion part. Okay, so let's find complement and supplement for these two things. For the complement, we know that this plus something has to give me 90 degrees, or pi halves. That's the same as 90 degrees, but in radians. Okay. So one way to do it, if you had it with a in degrees, you would say, well, I'm going to subtract just 90 minus whatever this is, and that gives me the answer. And it's the same thing here. So we're going to take pi halves and we're going to subtract this one, 2 pi over 5. Okay, and just like the one before, we have to have common denominators. So I'm going to go ahead and kind of do my little butterfly trick here because I noticed that 2 and 5 don't really have much in common. So I'm going to multiply this one by 5 and this one by 2. So I can get a common factor on the bottom. So that will give me 5 pi over 10 minus 4 pi over 10. And now I have the same denominator, and I can go ahead and subtract. 5 pi minus 4 pi equals 1 pi over 10. And that's it. So this plus this equals pi halves. If I put these two pieces together on a circle, it's going to make a quarter of the circle. So something like that. Pi tenths, 2 pi fifths is going to give me that quarter of the circle. Okay, let's try the supplement now. So supplement is going to be the 180, right, or pi. So the supplement is pi, because pi is half of a circle. And that means we're going to subtract pi minus my 2 pi fifths. Okay, so this one is I think it's a little easier because it's got to put it over 1, right? And common denominators would be times 5 because this one is a 5. So that's going to look like the following. 5 pi over 5 minus 2 pi over 5. 5 pi minus 2 pi is 3 pi. So this would be my supplement. This one plus the other one plus 2 pi fifths is going to give me the one that's going to add up to 180 or pi. And this one should make a little bit more sense because if you think about it, 2 pi fifths, it's like saying, so here's like half the circle. This is 1 pi, right? If you have two slices out of here, so 1, 2, and they're in fifths, so 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, there's 5 pieces, right? That's what this means. There's 5 pieces. And if we have 2 of them, well, we need 3 more to make the 180. So 3 pi fifths. So another way to think about it. Okay, second problem. 5 pi over 6. So let's find the complement. The same way, we're going to do pi halves minus 5 pi over 6. Okay, so just like we did before, we're going to do our little butterfly. Do this side times 6 and this side times 2, which is going to give us 6 pi over 12 minus 10 pi over 12. 6 pi minus 10 pi is negative 4 pi 12ths. What happened? Okay, so this is kind of important because we should not end up with a negative answer. Let's look back at the definition. It says two, and I didn't write this, I put a little plus, two positive angles whose sum is pi halves, which means that our angle has to be positive for this to work. So why did this one come out negative? It came out negative because 5 pi 6 is bigger than 90 degrees. This is going to be bigger than pi halves. If we look back at our little cheat sheet here, here's pi 6, okay? Notice that our first quadrant, so in other words, this right here, this is our pi halves, our 90 degrees, this little quarter. 5 pi 6 is not in there. 5 pi 6 is way over here. So you're thinking an angle from here all the way to here, which is pretty wide. It's an obtuse angle, right? This is way bigger than 90 degrees. So that's why this one is not going to work. So this one has no complement because 5 pi over 6 is greater than pi halves. It's too big. Okay. What about a supplement? Well, we saw where it was located already, so it is good. It's not bigger than 180 or pi. So that means we probably can find one. So supplement is pi, so pi minus 5 pi over 6. Let's work that one out. Put this over 1, multiply times 6. So I get 6 pi over 6 minus 5 pi over 6, which is just 1 pi over 6. And again, that makes sense because if we look at it, where's 5 pi? Here is 5 pi, here is pi. It's pi 6 away from the halfway point. So we are good to go. Okay. We're going to talk about now degree measures. So we've talked about radians for quite a bit. Degrees are the ones that you're more familiar with. 90 degrees, 180 degrees, 360. Okay, we should know in the circle, and again, I'll just use the one that we've been kind of using, the pi 6 one. If you look at the degree measures, it's 0, 30, 60, 90, 120, 150, 180, and so forth, all the way till you get to 360. So this one we're more familiar with. So what I'm going to show you here is how to convert from one to the other. To convert from degrees to radians, so what we know to what we're learning right now, you're going to multiply the angle times pi radians over 180. To go backwards, so then you're going from radians to degrees, you take the angle, okay, so the radian measure, whatever the pi is, times 180 over pi radians, okay? Please note that pi radians is 180. In other words, half of the circle is equal to pi, okay? Because the full circle is 2 pi r. Let's do some examples. These are not that bad. Let's just do these pretty quickly. So number 4, degrees to radians. So for degrees to radians, I'm looking at theta times pi radians over 180. Okay, so we're going to plug in our radian measure, our degree measure, which is 60. So 60 times pi radians over 180. And typically what we do is we just simplify the numerical part, this part. So 60 over 180 is going to reduce, let's see, by 60 actually. So I'm going to have pi over 180 divided by 60 is going to be 3. So pi thirds radians. And that makes sense because if we look back at our charts, man, this chart is kind of handy, huh? 60 degrees is the same as pi thirds. So we are good to go. Okay, let's look at example or letter B. So now we have 320 degrees and we're going from degrees to radians. So again, using the same little conversion here. Okay, we're going to take our 320, that's the degree measure. Should have put the degree here. So 320, you can put it in parentheses or not, it's up to you. Pi radians over 180. And we're simplifying, again, the numerical part that's not pi. So this part right here, 320 divided by 180, you're just simplifying a fraction. So how can we simplify that? Let's see. It looks like I can divide them by, I want to say 4, 8? No, let's try 4. So if I divide this one by 4, I get 80 pi radians over 180 divided by 4 is going to be 45. Okay, and I can probably still simplify that, right? Because I can divide both of these by 5. So 80 divided by 5, I want to say is 16. So 16 pi radians over 45 divided by 5 is 9. So there is our answer for that one. And of course, you can use a calculator to help you with the calculations. That is okay. Just, you don't want decimals, you want fractions. Now we're going backwards from radians to degrees, which is what a lot of you are going to want to be doing because I think we're more comfortable with degrees. This one says to do the radians times 180 over pi radians. Okay, so it's going to look like the following: negative pi, excuse me, pi 6 radians times 180 over pi radians. And I notice it doesn't say radians here. It's implied. If you have a pi, it's going to be in radians, okay, for the most part. So from here, we can see that we can take out the radians because they're diagonal from each other, one on top, one on the bottom. We can take out the pi's, and we're left with negative 180 over 6, okay, which simplifies to divided by negative 30 degrees. You do want to put the degrees for this one because you're going from radians to degrees, okay? Again, let's look at I know pi 6 is on here, so here's pi 6. Let's find negative pi 6. There it is, negative 30, negative 30, okay? Last one, 5 pi thirds. We're trying to go from radians to degrees, so same thing. We're going to do our degree measure, so remember this is radians. So 5 pi thirds radians times 180 over pi radians. Okay, the radians are going to go away, the pi's are going to go away. So I'm left with 5 times 180 over 3, okay, which is going to give me, let's see, 180 over 3 is going to give me 60. 5 times 60 is 300 degrees. Which I'm pretty sure if we check with our chart, because remember the 3's are on there, the pi thirds are on there, is going to match up just fine. Okay. All right, last but not least, we have an application problem. So this one, I think there's this one, yeah, the one after this is going to be done in class, hopefully. This one has to do with arc length and area of a sector of a circle. This is 2 of the applications you're going to be seeing for these types of problems. Before we do the problem, though, we have to have some formula here. Arc length is basically the radian measure times the angle. I'm sorry, radian measure times the radius. So whatever the r is, that's going to be our radius of the circle. The theta, which is this symbol here, is the radian measure. So you're thinking something with a pi. Okay. Area of a sector of a circle. This is like, think of a pizza, it's the pizza slice, okay? Is 1/2 r squared times theta. So it's kind of like I guess kind of like well, I don't want to say triangle, but it's somewhat related to that, where you're going to take our radius, square it, and then multiply it times again the radian measure. Okay, so let's go ahead and look at this problem. It says a sprinkler sprays a section of a golf course a distance of 50 feet and rotates through an angle of 120 degrees. Find the area of the land sprayed and the arc length. So the area of the land sprayed is kind of like your slice, and the arc length is the top part. So we're looking at, just so you can kind of see a picture of this, we have this sprinkler, right? I don't know what they look like. I don't know, something like that. And it is spraying water across this section here. So it's kind of like that. So all of this is getting wet, this part of the golf course. They want to know, so this part right here, that's the arc length, which we denote with S, arc length. And then all of this part is the area. Okay, so that's what we're looking for. We're looking for those 2 things. Notice that, and they told us also, sorry, that this right here is 50 feet. So that would be our radius, that's R. The angle is 120 degrees. There's a problem. This is in degrees. Our formula says we have to do this in radians. So the first thing you need to do is convert this one. We're going to convert 120 to radians, because for us to use the formula, we have to use radians, okay? So let's do that first. Radians to degrees is going to be radians times 180. Oh, wrong one. I'm sorry. Wrong one. Is theta times pi radians over 180 degrees. Okay, so let's plug it in. That's going to be 120 times pi radians over 180. And we have to simplify this. So 120 over 180, let's see, I can get the zeros, it reduces by 6. I'm looking at 2 over 3, so 2 pi thirds radians. Okay, this is the conversion. The conversion. Okay, now once we have our theta, so this is theta. Okay, this is the angle. Once we have this, we can plug it into our formulas. So S is equal to r theta. This is the arc length. So our r is 50 feet times theta, 2 pi thirds radians. And we just multiply. And for this one, you probably do want to get a decimal. Just, it kind of depends on the problem. Um, so it would be 50 times 2 is 100 pi thirds feet per radian, I guess you could say, feet radians. Get the decimal equivalents, just about 104.72 feet. Don't worry about the radians for this one, because we're just looking for an arc length, which means it's just a one-dimensional, or two-dimensional, I should say, measure. Okay. For the area, so now we have A equals 1/2 r squared times theta. 1/2 times the 50 feet squared times our radian measure. I went ahead and I just took off the radian because we know it's in radians, so we don't really have to write that twice. That's going to give us 1/2 times 50 squared. So 50 squared is 2,500. Okay, times 2 is going to be 5,000 pi over 6. Okay, and we just simplify that. So I'm getting 2617.99, and this is in feet squared because it is an area. And yeah, that's basically it. Okay, so that's how to find, I mean, they're pretty self-explanatory. This is the formula for arc length. So let's write that down. This is arc length, and this one is the area of a sector. So like the slice, okay? And that's it, guys. That's it for this video. If you have any questions, as always, let me know.